For the past 7 months, Cornell Mars Rover has been designing, building, and refining a rover ready to take on URC. We're thrilled to introduce this year's rover, Cayuga. This year, we prioritized an early build to maximize testing and deliver our most reliable rover yet.
Considering our team's experience designing and building 6 degree of freedom robotic arms, we chose to build a more optimized version of our previous year's arm that includes additional features. This year, our arm features a quick swap end effector system, which has given us the freedom to design a special end effector for each mission. Our end effectors are distinct, with one designed for precise manipulation, another for picking up large and irregular shapes, and a third for soil collection. We redesigned all of our arm joints to move our arm's center of gravity closer to the base and simplify our wiring. Furthermore, we are working to implement torque transparency between our large-scale arm and our small-scale arm, so that our mini-arm operator can better interact with their environment.
Based on the performance of our previous rover, this year we have implemented a damped multi-link suspension. This change increases system rigidity, reduces vibrations, and allows for high-speed traversal over rough terrain. Our new 3D printed wheels are driven by Maxon planetary gearboxes and motors chosen to enable high speeds while maintaining precision control at low velocity. Swerve drive allows the rover to move omnidirectionally, significantly enhancing maneuverability and fine positioning. To extend communication beyond line of sight, we have developed a network of radio repeaters that can be deployed off the back of the rover, eliminating reliance on point-to-point communication. We have also developed a custom drone to act as a scout and carry out tasks during the extreme delivery mission.
This year, we redid our communication system by swapping out CAN 2.0 to CAN FD. By doing this, we have transitioned our communication system to be simpler by using the FD CAN USB board from MJBots. Our team also designed custom PCBs for any external hardware that requires specialized electrical control. Our new servo board supports 16 servos, and our new brush motor driver runs 6 motors compared to our 2 motors supportability in previous years. We also bought new radios with point-to-multipoint compatibility to support our radio repeater system.
This year, we have swapped out our autonomy algorithms for the Navigation 2 stack. This will allow us to leverage the Nav2 framework for optimized path planning algorithms. We have also invested in a LiDAR camera for laser scan data and obstacle detection. With the Z camera, we're now able to use the Z SDK to collect positional data estimates on detected objects, such as the mallet and water bottle. Furthermore, we have designed a Move It To inverse kinematic stack to efficiently navigate our robotic arm for any task that requires precise end effector navigation.
This year, we have expanded our science payload, including more assays than ever before, to identify the presence of extinct and extant life in our soil samples. We use fluorescamine in conjunction with our in-house fluorescence spectrometer to detect primary amine groups in soil. We also use an anhydrous assay to detect proteins in the sample after being heated, and we use Alamar Blue as a metabolic indicator to identify actively metabolizing life, and both of those tests rely on visible light detection for analysis. We use a low-concentration acid to detect extinct life, which we supplement with additional sensor data and camera feeds to draw conclusions regarding habitability and the presence of life in a given sample area.
The Astrotech subteam is focused on creating a life-detecting science array in order to analyze soil samples on board the rover.
This year, we are using our 6 degree of freedom arm and attached scoop to dig at soil sites. Each soil sample is then separated into different chambers. One part is sealed to deliver to judges, while another part is mixed with low-concentration acid, which would react with fossil carbonates if present. The rest of the soil is combined with a neutral solvent, filtered, and passed through a series of chemical tests. Then the sample undergoes visual inspection and later is pumped into a cuvette for analysis in our custom onboard spectrometer.
To ensure reliability, we've developed a rigorous testing plan. The team is divided into 4 task teams, each dedicated to a URC mission. Each team follows an incremental strategy to bring the rover to full functionality. Our testing sessions also cross-train members for operations and rapid repairs. With modular systems, teams can experiment with slight design variations to optimize performance. These teams have already begun strategizing, verifying reliability, and preparing for 2 full-scale mock competitions, giving the competition team real-time experience under pressure.
Testing proves that on this rover, engineering meets execution. This is Cayuga.